we observed exactly how they were driving. What you see on the right-hand side on this chart is the difference in speed on the x-axis and the distance of the two autonomous vehicles, which are the Prius 1 and Prius 2 in this case, and how they have different distance when following at different speeds, which identify the color. And what you see in different scenarios, so one was the connected scenario of these two following each other, there you could see at speed of 120 kilometers per hour, they were having a distance between the two vehicles of 14 meters. And you see also they oscillate a little bit, so they don't exactly drive the same speed, nearly exactly, but only a little. In case of if connectivity is switched off of these two autonomous vehicles prototypes, they switch to a headway of around 40 meters. And you see also here in following modes, their speed differences is going a little more strongly oscillating when following each other. So these are the results we obtain from these tests within Coexist. And in another picture, you see the relation between vehicle speeds in kilometers per hour. So how fast are they driving and what is the distance what they keep to each other. So this is a non-connectivity example. And you see here a linear relation of speed and the distance to each other. And for those of you who are experts in Vissim will directly know this is Wiedemann 99, where we have this linear relation. But what we try to do is to replicate and to extend our driving behavior so that the observation, what we found in the field test, can be replicated in the simulation software. So by default, if you take the default values, this is how it looks like for Vissim vehicles. And it's because of this high stochastics in there, in following, in putting the braking pedal, the throttle, and having a variance in speeds in this oscillation. So there's high stochastics in following, which we don't see for autonomous vehicles. And that's why we have new automated vehicle behaviors added to PTV Vissim to achieve validation against these real-world public tests from automated vehicle data. So what are these new functionalities? First, there is 3, and you'll find them in the defaults, but also in an additional example, there are 3 more driving behaviors in PTV Vissim. This is AV cautious, AV normal, and AV all-knowing. And these driving behavior were introduced within the project Coexist to replicate different assumptions of behaviors. So cautious driving logic is driving very safe, keeping a higher safety distance compared to normal human drivers, what we observe today. They respect the road code, and they keep a quite high safety distance. We call it the brick wall distance. I'll explain that in a second. The normal driving logic replicates a kind of normal behavior as we see it in human in terms of a headway, what kind of distance they have to the leading vehicle. And but of course, removing all the stochastics, what we see. So they drive all exactly, they take the same acceleration when in the same situation, whereas different humans will have different acceleration, for example. And then the third one is the all-knowing driving logic. It's a little bit more aggressive driving logic, so it keeps smaller headways, and it also knows the information from the leading vehicle. So in this case, for example, if an all-knowing vehicle is following another all-knowing vehicle, it gets the information. So it's connectivity leading to smaller gaps, and what you can also see in these numbers of this example. It doesn't really need, it knows everything. In Vissim, the vehicle will not know everything what's around it, but it's more the assumption this vehicle knows exactly what's around, and therefore it optimizes only his own path to the destination and driving a little bit more aggressively. All these parameters, and you see there we have some default parameters for that, but it's not like you should not change it. You should make, if you take this driving behavior, you should make your own assumptions in terms of what kind of distance do they keep following at a certain speed. So the first option is the one I just mentioned with brick wall stop distance. We call it within Vissim enforced absolute braking distance. This means if a vehicle follows another one, and if the right vehicle will change its speed from like 100 kilometers immediately to 0 kilometers per hour. So maybe because of a false detection or something, the vehicle will stop immediately. Even then, I guarantee I keep a safety distance that this vehicle is able to do emergency braking and stopping in front of the vehicle. So, and that of course always leads to much higher distances, but you can activate it in Vissim. The next option is the number of interaction vehicles and objects. Previously, we only had the number of interaction vehicles in Vissim, and that was then a mixture between vehicles and also signal heads, for example, were taken into account, or speed decisions. So now we splitted these two because of one reason. But first I'll give an example. The interaction objects 4 means the vehicle will see 4 objects in front of it. So the first car, the second car, the signal head, and the third car. And if interaction vehicles is 4, it sees also as a maximum to 4 vehicles. Now, because of there's one signal head in between and the interaction object is only 4, it cannot see the 4th vehicle, but it sees a maximum of 4 vehicles. So if we limit the interaction vehicles to only 1, but keeping the interactions objects to 4, this vehicle will only see 1 vehicle. That might be because of some kind of sensors, so that an autonomous vehicles will not be able to see further than this 1 vehicle. But what we still want to guarantee is with interaction objects 4 is that this vehicle can see the next signal head because of connectivity or other reasons. So now you can make this separation between objects and vehicles, which was previously not available. A new functionality is also the headway based on class of leading vehicle. This means if we have different vehicle types, and assuming the first one here is connected, and if they are connected, they can keep smaller headways. But if this connected vehicle is following a conventional vehicle which is not connected, or an autonomous vehicle which is not connected, it needs to leave a longer distance because it doesn't know the information what this vehicle is doing. And also following by to another human-driven vehicle. So in the driving behavior parameters, you can set for a specific driving behavior that if the vehicle follows a conventional vehicle, you can define what kind of parameters for VDMAN 74 and VDMAN 99 is kept. And if it's following another vehicle, which may be not a connected vehicle, then having larger headways. And this is available for all driving behaviors, not only for the autonomous driving behaviors. So for example, if you want to model that a normal human-driven vehicle is following another human-driven, it keeps a normal headway of 0.9. But if a normal vehicle will follow a truck, it will keep a higher safety distance. Then the other option is use implicit stochastic, meaning before there were still stochastics within the driving behavior which you were not able to influence. So you were not able to really replicate the same behavior for the same situation for the same vehicle. There were always stochastics internally. And now you have a checkbox where you can switch it off. and then the vehicle will not use of this implicit stochastic. That was used for how the braking pedal and the throttle is being pressed, for example. Another thing we saw when calibrating this model to this real testing is that they were accelerating quite strong when they were connected compared to our default driving behavior. That's why we have introduced increased acceleration to really that the following vehicle is able to keep up when they accelerate. So typically it's 100%, of course, but you can increase it or even decrease it. And a very simple one, but now for occupancy distribution, you can use the value 0, meaning no human driver is in a vehicle, which we're not able to do before. So far from the autonomous vehicles functionality, and I'll switch over to Alistair to go on.
Okay, so we have also a number of features which allow us to take better control of pedestrians and vehicles whilst a simulation is running. And the first thing that I wanted to present on this topic is the inclusion of attribute decisions within the simulation. Now, what attribute decisions allow us to do is actually change the attribute of a pedestrian as a simulation running or of a vehicle as the simulation is running. So here we can see pedestrians entering a network, and once they reach a certain point in the pedestrian area, you can see them changing color. And that is where they're being assigned an attribute. And that attribute might be that they need to buy a ticket. It might be that they want to have some food. It might be that they want to get a newspaper. And we can completely open this up. So we could also have pedestrians who need to run to get a train because they're late. And then we can also apply it to vehicles as well. So we can apply different attributes to vehicles as the simulation is running. That could be vehicle occupancy, it could be vehicle speeds, we could even change vehicle behavior as well. And once we've given those pedestrians or those vehicles new attributes, we can then start to actually control and influence what they actually do as they are in the network and as they're navigating through the simulation. So an example of that here for pedestrians, we are showing that we have attributes which could be pedestrian height, and this video is demonstrating that pedestrians that have a height over 1.65 meters, for example, are too tall to walk through a doorway and therefore are walking around, whereas pedestrians who are a little bit shorter are able to walk through that doorway. So this demonstrates how we can actually take those attributes of those pedestrians and influence the route and the journey that they're taking through the simulation. Now, we can also do the same thing for vehicles as well. And here I've just got a quick demonstration model open where we have a link structure and we have 5 different destinations on the right of the model. Now, once we start this simulation, we can see that vehicles are entering the network and they are routing to the different destinations, and we're color coding those vehicles. Now, if we stop the simulation and just run it on, we can see that as vehicles enter the network, they're black. And so they currently don't have a destination assigned to them. And if I actually select this vehicle and we go into our quick view, we can see here under destination that there is no destination assigned. Now, as the simulation moves on, we have a vehicle attribute decision located in this area. And if we look at that vehicle attribute decision, it's providing a distribution between 1 and 5 to actually assign a destination to that vehicle. So we have a new distribution within Vissim 11, which is a free distribution. So that allows you to actually define whatever distribution you want. So we could define 10% of vehicles going to destination 1, 30% to 2, and so on and so on. And as the vehicle actually crosses that attribute decision, we can see that it changes color. And now when we select that vehicle, we can see that its destination is destination 2. So that's how an attribute decision can be used for a vehicle and a new attribute assigned to that vehicle. Now, linked to that is how we can influence the route of that vehicle. So here we can see that we have an upstream static route decision. Now, what you'll notice is new in Vissim 11 is that you have a different route choice method for static vehicle routes. So you're used to seeing static as the route choice method, but we now have something called formula. And that formula allows you to enter a free formula into how you would like to control that vehicle. So here we have our two different route options, and we have a very simple formula that looks at the destination. So this destination being that attribute of that vehicle that we're showing here, and then taking that destination and saying if the destination's below 3, then turn left to access the 3 destinations. If it is above 4, then turn right, because that's the route for those. So as that simulation runs, you can see those vehicles start to move through the network. And we're also able actually to change those attributes as we go as well. So here we can see that as this simulation runs on and the vehicle actually routes to a certain location, it's now moving towards routes number 4 and 5. But if I change this now to route 2, we can see that the vehicle changes to route 2. I have another routing decision. And as we run on now, we'll see that this vehicle actually takes an alternative route and goes up to its destination as well. So it really allows us to have a lot more control over how we route pedestrians and vehicles through the model. And that gives us a number of different use cases. So for instance, we could look at things like toll booths, and in toll booths where we have people that pay by credit card or pay by cash, we actually could then model more accurately airport forecourts, for example, where we have different doors assigned to different airlines. Clearly, we could give different vehicles the attribute of a different airline code and then route them accordingly to a certain pickup and drop-off area associated with that code. Same thing with autonomous vehicles or mobility as a service, where we can attribute vehicles that could be certain rideshare providers, routing those to certain areas in car parks, certain pickup and drop-off zones as well. Okay, another feature we wanted to run through with you today is the managed lanes inclusion within dynamic traffic assignment. So previously, the managed lanes functionality provided an alternative route for vehicles within a corridor, and it was a localized decision. So what that meant was, well, whilst a vehicle was on a corridor, it would make a calculation whether to use a managed lane or a general purpose lane, depending on the certain cost of that managed lane and various kind of coefficients. Now we've included that whole decision process within dynamic assignment as well. And what that means is that vehicles will actually evaluate the attractiveness of the managed lane corridor against a wider alternative route, so against parallel routes as well. And that means that where we are looking at forecasting for managed lanes, or where we're looking at implementing new managed lanes, we can actually start to understand the impact of that introduction of a managed lane across a wider area. So we can look at whether or not we see a redistribution of traffic from parallel corridors onto that managed lane, vice versa, actually taking traffic away from that managed lanes onto parallel corridors if parallel corridors are performing better. So that really gives us to the ability to better evaluate the capacity of managed lanes in the future, and also look at the impact of pricing from managed lanes on surrounding routes as well. So those vehicles are able to make their decision about the route through the network, of the attractiveness of the managed lane corridor, as well as wider alternative routes as well. Okay. The next few features that I'd like to run through focus on visualization and visualization enhancements that we've recently brought into the software. So the first one that I'd like to discuss is the ability now to add 2D labels for vehicles. So here we have a simulation running, and when we go to our graphic parameters of vehicles, we can see that we add a label visibility. Now here we could show speed, but I could also, for example, show the current delay time that a vehicle is experiencing. So now we're actually demonstrating the delay time of every single vehicle. We can change the color of that label, we can change the size of the font, we can change the number of decimal places that data have. but it allows us in real time to actually see some statistics and see some actual attributes of the vehicles and be able to label those as the simulation is running. So again, that could be speed, it could be delay, it could be vehicle occupancy, any types of different levels of information of those attributes of the vehicles. You're able to actually now label and see those as the simulation runs as well. Similarly, we also have 3D info signs. So now if you would like to record a 3D visualization video, and maybe you would like to add an info sign to identify a certain junction, it might be that you'd like to add a info sign above a junction that has the name of that junction, the level of service, the delay, the average delay that vehicles are experiencing, then you can freely enter an info sign and have that actually located within the network editor. Likewise, you can add info signs to vehicles. So again, showing maybe the vehicle number or the vehicle speed, and actually have that as a kind of flag that is above the vehicle as it moves through the simulation as well. So different ways that you're able to demonstrate and provide information about different vehicles and pedestrians in the simulation, again, as the simulation is running. Okay, another feature that we've implemented is the ability to visualize queue lengths. And this can be done either by using node evaluation or by using individual queue counters. So this will help you to actually identify where you have spillback potentially within a junction, or just visualize really how long queues are at certain intersections. So here we can see in blue, we're demonstrating the queue length that is shown within that time interval of the evaluation, how far that queue actually stretches back along the link, and then also adding a label to demonstrate how long that queue is. So you're getting the empirical information as well. And that can be shown for queue length maximum, it can be shown for queue length average, lots of different queue characteristics as well. And you'll see here that there's actually a spike within this node. So where a queue length actually extends back into the node, this spike demonstrates that that queue would extend further than the node is showing. And here you can actually see that queue popping out the other side of the node as well. And so those labels, those numerical values that are shown there are taken from the standard queue length evaluation as well, but represented graphically on the network. So you can demonstrate that with different colors. Here we're just showing it with blue, but we can show it with red, and all of the standard graphic parameters are available to you as well. Okay, and here is just a video which shows this live. So we can go into our queue counters. We show our queue lengths here. I'll select the queue length maximum, the current time interval, and you can see that's actually where we activate that queue length counter from. And as this simulation runs, we can actually see those queue lengths starting to build as the vehicles are there. And again, we can change the color of those and actually demonstrate them to be red. So here, demonstrate changing that color. Maybe we'll put it as red. And again, we can see within that time interval the data changing as well. Okay, the final feature on visualization is that we now have the ability to include keyframes within AVI recording. So this is a really powerful feature where you have lots of different evaluations and lots of different network editor layouts that you want to present within a simulation. So here we can see a number of pedestrian evaluations that are actually being run through keyframes. So we're allowed to set up all of our different keyframes within the model. We have our start time, our dwell time, and then actually adding our network layout as well. So presenting all of that different evaluation and having the control to actually define all of the different views and all of the different keyframes and network layouts, and just having those cycle through as we create our AVI recording. So it gives you a lot more control about the data that you'd like to present. and demonstrating actually building a storyboard of your AVI recording, demonstrating exactly the information that you want to present and how you can cycle through those things as well. Okay. A big feature that we've been working on for a while within PTV is how we can better tie integration with PTV Vissim. And this is particularly focused on the use case where we want to share networks and share assignment results and routing data from PTV Vissim into Vissim. So here you can see that I have a network that has been imported into Vissim through ANM. So we have taken this network, exported it from Vissim and imported it into Vissim. And if I go to my vehicle routes and my static vehicle routes, I can see that I currently don't have any route information in there. So it's just a network. Now, when I go to import, I've got a new option called RCF, which is a route coordinate file. And I can bring that network in as a static or dynamic assignment. And once I actually import that, you can see that all of my static routes have been populated. So here I now have all of my routing information, but it could be that I actually zoom in on a particular junction and I notice that I don't like the geometry of that junction. It might be that through the import from Vissim, there's a certain mistake. Now, I can delete that junction and recode it so that as a microsim modeler, I'm a little bit happier with the alignment of that junction, adding connectors, and actually being able to represent the geometry of that network a little bit more accurately for microsim. Now, the problem is that in the past, this breaks the route connection from Vissim to Vissim because we're changing the node structure. And you can see here that we now have errors which say the network is not complete. The feature that we've developed means that now we can actually re-import that route coordinate file and it just snaps back on top of that network. So now once we've imported it, we can actually see that all of the left-turn vehicles, the straight-on vehicles, use the new link structure that we've implemented rather than actually us having to go back into Vissim, make that change, re-export the routing as well. So it allows us to have independent link structures from Vissim and Vissim, but still be able to pass route information, assignment results, traffic volumes between the two. So this could be that you've completely developed your networks in parallel and you just want to pass those assignment results between the two of them. It could also be that you have done, as I've shown in this video, where you just notice that there's a mistake in the coding and you need to correct that, and therefore you need to re-import that route coordinate file. But it actually allows us to detach that routing from the network structure and have it based on coordinates. And there's a certain ability as well, a certain allowance for how the networks snaps, so the networks don't have to be geo-referenced in exactly the same place. There is a slight tolerance that allows us to also still use the route coordinate file even when the networks aren't exactly on top of one another as well.
Now some selection of functionality which we did for the usability. The first one, is a very helpful tool is filters in lists. So we like very much working in lists. Now, as you maybe know from Excel or from Access, you can simply activate it on top of the list, a filter. And depending on the data type, so for example, if it's a text or if it's a number or even a color, there are different options on how to filter. For example, equals exactly a specific vehicle type, or in terms of a text, if it contains a certain text, if it starts with a certain text, or for a number, if it's larger than, smaller than, and so on and so on. So you can have multiple filters, even for multiple attributes. And of course, in the named list layouts, which you can here just enter a certain name, you can save even this configuration of the list, including the filters. So you can save these filters and easily switch between filter, no filter, other filters. So that's the first very useful tool to filter some lists. The second one has been requested for quite a while. So now in the two-dimensional network editor, there is a measuring tape, and the measuring tape will allow you to simply measure distances between 2 points in your network. But as you see in the video, also between along a certain link or link connection along a certain route with some intermediate points, and you simply can measure it now using the measuring tool. The next functionality is quick info. So in the user preference of the network editor, you can activate the quick info, which is activated by default. And whenever you hover through the network editor, it will show you directly the object name, the object number, and when you edit something like adding a new link, you see already the link length. And there's even functionality that when you create something, when you edit something, that you can even enter different values. For example, if you enter a circular link or a circular area, you can enter the radius, for example. Then very simple. So in drop-down list, if you have a lot of signal heads in your network and you need to select one in signal head, and you enter 137, previously you were entering at signal head starting with a 7, because 7 was the last number you were entered. But now if you entered it quite fast enough, 137, you end up at 137. Quite simple, but very useful. Then a bigger change is now in the attribute selection dialog. Whenever you need to select an attribute, for example, to configure your list, you see this new dialog, and it holds quite a number of new functionality. The biggest functionality, the most useful, according to myself, is the search for attribute name. So if you enter some letters in the search bar, it will automatically update only the attributes which contain the letters which you were entering, or not only the letter, but also the letter sequence. You can switch between alphabetical order or semantic sorting. You can directly create user-defined attributes for this specific network object. You can add and delete and also edit aliases if you make use of them, which I recommend to use. You can hide some columns on the right-hand side. You can group attributes. For example, you only want to add all user-defined attributes to, for example, your list. And you see also which one are already selected on the right-hand side from the left-hand side list. Multi-selection is now also supported. So as in the Windows Explorer, if you hold the Shift button and multi-click to some attributes, multi-selection is able now. Yeah, as I mentioned previously, we have now circular areas. So if you create an area, you can select to add a circular area. And as mentioned before, in the quick info, and this identifies the blue rectangle, this is an editable field. So if you add it, you can directly enter a number, and then it will create an area with a certain radius. Okay, now coming to pedestrian simulation. What are the new functionality? We quite did a lot on pedestrian simulation. The first one, which is linked to visualization, is 3D models with luggage. I need to say that the behavior is not changed, so they still behave differently. They may have different sizes, of course, but it's no specific behavior. But just for visualization issues, you can now show some with a backpack or a trolley. Another feature which goes into the direction of shared space. So if you want to model the interaction between pedestrians and vehicles, vehicles are now considered in the navigation of vehicles. So you see here pedestrians crossing a street, and when the vehicles queue here, the pedestrian, they still try to walk straight from their origin to their destination, and just standing in front of the vehicle and not being able to work around. This is when the dynamic potential is switched off for the vehicles. But if you activate that the vehicles are considered in the dynamic potential, maybe explaining dynamic potential is a calculation method, how the vehicle will walk towards its destination, then the pedestrians, they see the vehicle and they go around the vehicles, so they walk much more intelligent towards their destination. And in wherever you have crossing, but specifically goes towards shared space, so that you can model with higher precision these facilities. Also, combining with the dynamic potential, it's now also activated on waiting areas. So if a pedestrian walks towards the position, the waiting position on the waiting area, it also considers obstacles which haven't been there before. And the same thing is also for boarding. So in a second, we'll see a public transport, a train, public transport vehicles entering. And when they walk now towards their boarding position, also they are able to see the obstacles. So they are considered in the pedestrian routing. We have new network object. We have extensions to the network object stairs. We have different stairs, like you see the ones 90-degree landing, a U-turn, and this intermediate landing here. And they can be configured directly in the ramp and stairs network objects. So there's these additional attributes for flight 1, flight 2, flight 3, the length and the width, and you can enter them to create them. Also, if you import from BIM, from building information model, you can directly, they have it in their standard, this kind of stairs, so you can directly import them from there. Also related to stairs, now pedestrians are able to use a dynamic potential on stairs, or not only stairs, but also ramps, to walk a little bit more intelligence. But again, dynamic potential is always very, needs a lot of resources, time consuming, simulation will be slow, so there's always the option to switch it off in order to achieve higher run times, but maybe not so good results. As you see here on the left, the standard where dynamic potential is switched off, where they often face each other. But with this activated dynamic potential, they try to avoid the conflicts more precisely. And I think the best option is if also the option is activated that they should keep right on the stairs to have less conflicts. Another option is that on areas you have an additional speed factor. Just if you imagine you walking inside a building and then you go outside and then in another building again, and it's currently raining, you see most people will adjust their speed and walk faster outside while they walk through the rain. And something like that can be modeled if you just imagine this circular area now is an area where it's raining, and the pedestrian, once entering this area, they accelerate by a certain speed factor. So you don't need to set up new walking behaviors. You can directly on the area have an additional speed factor. Coming to the end of this webinar, we hope there are some attractive features for you as a modeler. PTV Vissim 11 is already available, so you can start using the features. In addition, there are new example models to explore, as you can see here, one for cable cars. We are looking forward to hearing your feedback, and we very much appreciate all your further feature requests. Additional material, for example, other webinars, can be found on our web page or YouTube channel. Should you have more questions, you can still ask them using the questions window. Alistair and I will stay online for a few more minutes and write back to you. For those leaving right now, all the best to you and enjoy modeling with PTV Vissim.